How is combined rotation and translation of vectors represented? Before we represent the vectors in rotation and translation, we need to know about frame. Mathematically, a frame is a set of 4 vectors giving position and orientation information. The description of the frame can be thought as a position vector and a rotation matrix. Frame is a coordinate system where, in addition to the orientation, gives a position vector which locates its origin relative to some other embedding frame. For example, in a frame, there is a vector P which lies in frame XB-YB, which itself is at an angle 30 degrees to frame XY-YA. The vector P here is represented by an arrow. An arrow represents a vector drawn from one origin to another, which shows the position of the origin at the head of the arrow in terms of the frame at the tail of the arrow. The direction of this locating arrow tells us that B is known relative to A and not vice versa. Mapping a vector from one frame to another, the quantity itself is not changed, only its description is changed. Let's now see how to represent the vectors mathematically. The dot product of vector can be represented as. The cross product of two vectors is represented as. A unit vector is marked as. A three-dimensional point is represented as. Once a coordinate system is fixed, we can locate any point in the universe with a 3-into-1 position vector by proper orientation. The components of P in A have numerical values which indicate distances along the axis of A. To describe the orientation of a body, we'll attach a coordinate system to the body and then give a description of this coordinate system relative to the reference system. Now let's understand the description of orientation using matrices. Let's represent the vector R, which lies in a frame, say B, which exists in another frame, say A. It can be represented as, where XB is the unit vector in B and XBA is a coordinate of a unit vector of B in coordinate system A. The rotation matrix is a translation vector that have 3 degrees of freedom in each coordinate frame. In this case, a total of 6. With respect to the vector P, it can be written as. The rotation matrix is represented as RAB. In order to represent the vector P, it can be imagined that the frame B to be away in space from frame A at certain distance, say ORG. So now the vector P can be written as. Now let's combine the rotational and translation matrix. We get the vector P as. In this way, the rotation and translation matrices are combined to represent vectors.